So very good. Let me make a brief recap, and in particular, let me open the web page of the course. 1 second, and then I share it. Tutorials of Harbour Engineering. Here we are. Let me share the screen. Okay, very good. Let me open the font so I can check if everything is displayed as I am expecting. Okay. Good. Okay, so now let's look at the list of the lecture. What we did so far was forcing estimation for Harbour design, as you may remember, and then we made the exercise computation of wind actions on a moored ship. When I talked about forcing estimation, I mentioned to you that in some instances for important projects, we may need to go beyond the empirical relationships, to go beyond the rules of thumb that I suggested to you. And I said that there are two main avenues in order to make a more detailed assessment. And one avenue is numerical modeling with 3D hydraulic models, and they may be also models governing, reproducing the morphodynamic of the coastline. So you have numerical models as an alternative, and numerical models are mathematical models. They run on a PC, and the advantage is that they are not much demanding in terms of resources, because you just need a PC. You don't need a big lab in order to make them. And the disadvantage is that numerical models are affected by uncertainty. There are approximations in numerical modeling and also approximations in the reproduction of the processes. But this is one possible avenue, which is today becoming more and more popular because you know, it's less demanding, as I said, in terms of resources. And then the other avenue, possible avenue, is the small-scale physical modeling. I mentioned several times to you that indeed this alternative. Just let me. Sorry, I want to change. Oh, no, okay, it's fine. I thought that I was using the wrong webcam. So small-scale physical modeling, as I said, it's an interesting alternative because it is reproducing in the lab what the real phenomena with a small scale model. It's a small scale because, of course, we cannot reproduce in the lab a full Harbour in its natural scale. And this is extremely interesting. It's very demanding. These models can be set up only in very huge labs. It's very interesting because we can really emulate what we expect may happen when the Harbour will be built up. And a problem is that when you reduce the scale of a prototype, the prototype is the reality. When you reduce the scale of the reality, in particular in fluid mechanics, when movement of water is involved, you get a distortion in the reproduction of what's going on. And the distortion is basically related to the more relevant role played by viscosity of water in a small scale setting. You understand that you cannot reproduce, for instance, turbulence in a glass of water, because in a glass of water, it's extremely difficult to develop turbulence because you have the viscosity that is playing a relevant role. Turbulence usually takes place in large spaces. And this poses a limitation to the scale. So you can reduce the dimension, the size of what you are reproducing in the lab. You can reduce it, the size, but not too much. And therefore, the result is that you need huge labs. Even if you work on a small scale, these small scales are usually 1/20, 1/30, 1/50. It's unlikely that you may get to a reduction of 1/100 because, again, the viscosity then becomes more and more relevant. But these models are an opportunity for the high costs, especially in setting up and maintaining these huge labs. They are usually adopted, they are usually built up in few research centers. In our university, we have a pool in the lab of hydraulics, which is not anyway very large. So we couldn't reproduce a full Harbour in that pool. I want to give you an example by showing you a video that now is linked in one of my web pages. And the video refers to the lab at Deltares. Deltares is a research company. They do consultancy and research activity, professional consultancy and research activity. They are based in Delft. I want to give you one video. I want to show you one video. This is, they have several bases there, and this is what they call the delta basis. The video is 5 minutes, and I'm not going to play now it for the whole 5 minutes. I am jumping, okay? I will start it and I will jump in order to take a couple of minutes of your time. And if you look at the web page of Forcing Estimation for Harbour Design, now I have linked this video, and I have also linked the web page of Deltares. Let me show you where it is. And it's, let me search in Google for Deltares. And here we are. I just want to show you the web page because there are, if you look on facilities, click on facilities up here, and let's click on it. Now you get these experimental facilities. There is a description. One of them is the Delta Flume, which I already have shown to you. It's this big flume where they create the very high waves. But then there are description of all of the facilities. They have what they call the Atlantic Basin, Pacific Basin, and the Delta Basin is the video that I'm now going to show you. These videos are interesting, so you may have a look. And let me close it and let me go to the video then, and let me start it. So this is a basin with large size, and you see that there are the wave generators on the sides. The size of the basin will be introduced soon. It will be displayed here. Let me see, let me jump directly to the description, technical description, and then I will stop there. I am jumping forward. Let me see where it is, because this is a perspective of the basin. You see that there are pumps for bringing water. And let me check where is, here we are. So let me pause it. So you see that it is 50 by 50 meters. So it's quite a considerable size. I mean, it's it's larger than an Olympic pool, an Olympic pool. And the max water depth is 1 meter. So it's not like a pool, it's less deep. And then there are wave generators, and there are the characteristic of the waves, and also they can generate currents. Let me move forward and let me show you some, let's see, some videos of real functioning. Here you can see the wave generator that is generating these waves, and you see that they can generate several types of waves depending on how they organize the movement of the wave generator. And here you see they are testing, you will see the details, they are testing a coastal defense structure. Let me pause it here. You see that this is a structure, it's a defense for an harbor. And it's realized with boulders, and you see that they use colors because they want to identify the location of the boulders, the original location of the boulders once they are moved, because you know these boulders can be removed from this structure, I would say that this structure is what it's an arbor defense. It's not really a groin. I'll define later what is a groin. And once these boulders are removed, they go into the pool, and then you cannot locate anymore their original position. But if they are colored, you can locate them. This is typically, it's a technique that is typically used also when making experiments in other settings for river hydraulics. Usually we put colored material in order to get also an idea of the direction of the flow under turbulence. Of course, if you can track the particles, the movement of the particles, then you get an idea of the direction of the flow. Let me now reproduce it again. You see they are generating waves in order to give a forcing on this structure. And I'm not sure what is the scale here, but I would say that you know, the pool is 50 meters. You see the different colors, and so I would say that this structure may be something like maybe 15 meters long, and 15 meters it's a scale that maybe 1/5, 1/6. Usually these structures are no more than, okay, they can reach 100 meters, but not more in the reality. In the lab, it's about, I would say 10 meters, so it's 1/10. And here you see an overall view. You see that there are several sensors here to monitor the wave height and to monitor the wave forcing. And here they are testing another kind of defense. Let me move forward. You see, and they are trying to assess the resistance of this defense. It looks like a defense made by concrete. And here you see an aerial view of this combined arbor defense. I think there is later another interesting issue that I want to show you. Let me move forward. And I think they were also testing, here, you see they are testing here the mooring forces. They put a ship there, and then they generate waves. And then you see that there is a mooring line, and these are the sensors that measure the forcing on the mooring lines. So this is a small scale model in order that is devised in order to analyze with details the mooring forces, because the procedures that we have taken into consideration, they are approximations, of course. And this is something that I believe is interesting that I want to show you. And let me see, I think you see this is a very huge facility. I think we are done. Let me just have a look. Yes, I think we are done. You see scale models tests for moored ships. 1 second. And arbor resonance. Yeah, you know, resonance, we mentioned resonance. It's something that indeed it's difficult to test if not with a small scale physical model. And it's if we are concerned about resonance, which may lead indeed to developing very important waves within the harbor, I think that the small scale physical model is a necessity. Okay, now let me close this, and then let me click on the next lecture, which is beach protection strategies and structures. So now we are turning to beaches. Just 1 second, I want to open another page and in a larger visualization mode, because otherwise, okay, I think, yeah, just give me a second. And what I was saying, we are now turning into beach protection. It is something that we already considered in the fall season last semester, but only marginally. In last semester, we studied, for those of you who attended, we studied the basics of beach hydrodynamics and morphodynamics. Here we are studying beach protection structures with the aim of learning how to design them. And because these structures can also be used to design the protections for harbors in order to create this, in the harbor, this sheltered area where the ships can moor without, in a easier way. So let me go to this page. So in order to study these structures, which, as I said, they have many things in common, we refer to the structure for the protection of beaches, which is something that is strictly related to harbor design, because very often when you build an harbor, you also have an impact of the harbor on the neighboring beaches, and therefore understanding how to design these protection structures in a wide context, meaning that understanding their functioning for the protection of the harbor and the protection of beaches with an integrated approach is the most appropriate way, in my opinion, to study how these structures should be designed. And what is extremely important for designing these protections, again, protection of beaches, protection of harbors, is the interaction that these structures have with waves. So let me now try to provide first a description of what I'm talking about, a description of these structures by subdividing them into categories. And so if you talk about interventions and structures for the preservation and maintenance of the morphological behaviors of coasts, even after the impact of human interventions, like, for instance, harbors, these protection structures can be classified into the main categories that you see on the screen. So first, what is the problem usually? The problem in an harbor is to make sure that waves are attenuated in order to create a sheltered environment, a quiet environment. And this is the target for the protection of harbors. And we will study how these structures interact with waves. If we look at the neighboring coastline, the target is to preserve its configuration. And in particular, we are concerned when in the neighboring of the harbor, like it happens in the Adriatic Sea, in the coast of Ravenna, we are concerned when there are beaches, because beaches, as we know, they have a relevant societal value. They have a relevant function for the economy, for the wealth of the societal setting in general, for tourism, and therefore, usually, what our problem is to protect them from erosion. Erosion, which is originated very often not very often, it's basically originated by human intervention. For instance, if you build up an harbor, you have to expect that in the neighboring coastline, erosion processes may take place, depending on the behavior of the currents, on the behavior of the waves, and on the behavior of the beaches. So what is the classification of this intervention I'm talking about? I think we can, when we talk about beach protection structures, we can divide them in 4 categories. The first category is managed retreat. And this strategy basically does not contrast the changes that are occurring. So this strategy does not oppose against erosion, but rather it's an adaptation to erosion. So if you have a kind of beach erosion, then you can manage a retreat. Of course, this is not always possible. And you manage the retreat in order to identify a new line of defense. This is not always possible because, especially if the context, the area is very urbanized, you cannot, of course, manage a retreat. But in some cases, it is indeed possible. And in some cases, especially close to Ravenna, it has been done. After the construction of ports, you have some erosion around the port and you manage a retreat. This can be done. And then a second category is interventions to hold the line, like seawalls, and we see many of them. So in order to stop erosion, we build a seawall, and then of course we get we don't have any sand against the wall. Usually we lose the beach, but still it's a kind of protection that allows you to keep the line, to hold the line. And then there are interventions to move the shoreline forward in the seaward direction. And this can be, for instance, breakwaters or groins. And finally, there is the category of the indirect measures, like, for instance, favoring the development of vegetation. They are also called green engineering methods or soft engineering methods or nature-based solutions. They are very popular today, and it is indeed a solution that preserves the ecological value of the environment. On the other hand, these solutions have to be managed very carefully because they are not hard interventions. So they need a continuous management, maintenance, a continuous monitoring. But indeed, they are gaining large popularity today because as opposed to the hard engineering methods, infrastructures, the soft engineering methods are more environmentally friendly, are more tourism friendly. They have less impacting visual impact, and therefore are, let's say, more environmentally friendly in general. Okay, now we can also divide the intervention in 2 categories, which are direct measures. Direct measures are those interventions that are used to move the shoreline forward. Okay, so you can call them also direct measures, and you call them also hard engineering methods. So these measures, the hard engineering methods include active measures, which modify the local hydrodynamic behaviors and therefore modify the sediment transport, and passive methods that protect the coast from erosion without modifying the hydrodynamics of the water. And therefore, let me make the classification again. We have this first classification in 4 categories, and in particular, the intervention to hold the line, okay, and to move the shoreline forward, these 2, are also called direct measures, as opposed to the indirect ones, which is the 4th category. Okay, so these direct measures include infrastructures, and they can be divided in 2 more categories: active measures, which modify local hydrodynamics, and passive measures, which basically protect the coast from erosion without modifying the local hydrodynamics. Let me give you some more details. Active measures, modify the local hydrodynamics. We have breakwaters, and this can be used also to protect the beaches, and can be used also to protect the entrance of harbors. And we have groins. So what are groins? Let me look at this Wikipedia page. I think you already know what is a groin, but let's see. Here you have an example in this picture. So the groins are perpendicular, are structures that are placed perpendicularly to the shoreline, as opposed to breakwater that are placed in a parallel direction with respect to the shoreline. What is the difference? It's very simple. The breakwater protect the coast and the harbor from the waves and the currents that are moving perpendicularly to the shoreline. So basically they are displaced in a direction that blocks, they are displaced in the longitudinal direction, and therefore they block the waves that approach the coastline perpendicularly. Good. The groins are perpendicular to the coastline, so they block the waves which are traveling in a direction that has at least a component that is parallel to the shoreline. So when you have waves approaching the shoreline at an angle, which means not perpendicularly, it means that the wave direction is not perpendicular to the shoreline, so it's approaching the shoreline at an angle. You have a component of the wave velocity along the direction of the shoreline. And therefore, in order to block this component, you need a structure that is placed perpendicular to the shoreline, as you see in the figure. And if you look at these groins, first keep in mind that, do you see here, there is the spelling with the Y. You can find in the literature both the spelling with the Y and the spelling with the E, with the I instead of the Y. The term is groin, and the I in groin can be a I or a Y. It depends on the US English rather than American English. And if you look at these groins that you see in the figure, you see that some of them are rectilinear. Some of them, like this one above here, it's T-shaped. So it has the shape of a T. It is like a combination of a groin with a breakwater, which is placed at the head of the groin. And the purpose is clear. You want to amplify the action, the protection given by the structure by offering a protection in two directions, perpendicular and parallel to the shoreline. And what is the advantage of these groins? First of all, you see what is the shape of the beach. If you look at the beach zones between each couple of groins, what you see is that the beach is U-shaped. In particular, in this case, my guess is that the waves, the dominant waves, are traveling in a direction that comes it's entering into the screen. And why I'm saying this? So I think that the waves, the dominant direction, the dominant direction of waves has a component from the town that you see in the bottom of the picture to the higher part of the picture. Why I'm saying this? Because I see that there is a deposition of sand in the part of the groins that is towards me, while there is less sand, there is more erosion in the side of the groins that is entering into the screen. And so why is this? Because the groins block the sediment transport. They block the along-shore sediment transport, therefore originating the deposition of sand updrift, which means the side of the groin that is towards you that are looking at the screen. This is updrift. And they induce erosion of sand downdrift, the side of the groins that is towards the screen. Now let me go back. Let me close this figure and let me see if there are other figures here, because this is a groin perpendicular to the shoreline again, but this is not a very nice picture. This is a wooden groin. You know, groins can be made by wood, can be made by concrete, can be made by boulders. And in particular, wooden groins are environmentally friendly, and they are frequently used. Of course, they need to be maintained and replaced when needed. The groins can be permeable. This one is not very permeable, but they can be permeable. If they have some permeability, they can have, if they are wooden groins, they can have windows. And the permeability may be useful because it's limiting their impact. And I will discuss this later on. Let me see if there are, other figures. So this is again a wooden groin, and this is not very elevated, but still it's a structure that is indeed playing a relevant role, because you can see that here there is indeed, even in this case, the structure is playing a relevant role. If you see, there is deposition of sand along the sides of the groin. This is precisely their functioning. They should originate deposition of sand in the sides, and there is more deposition updrift, and you may have some reduced deposition or even erosion downdrift. But still, when you see the groin that is accompanied by sand along its length, it means that the groin is indeed effective. And here you see a vegetated groin, vegetated groins, and again you see here the effect. You have this U-shaped beach, and in my opinion, if you remove the groins here, the coastline would get inland significantly, because I can see some signs of the coastline located probably around here. Look at my mouse before the intervention. If you look at the shape of this, you can recognize that there is a shape of old beach around here. And in this case, again, you have higher deposition in the side of the groin. Let's see, if you are over a groin and you look with your face to the sea side, you see more sand on the left than on the right. But still, even on the right, you have had, thanks to the groin, some deposition. More deposition to the left, less deposition to the right, but still these groins helped a lot to bring the shoreline forward. Let's see if there are other pictures, and I think this is also an example of a groin that may be used also to protect, to create a sheltered area. This is a long groin. It is getting a long distance into the sea, and it's therefore creating a protected area. Indeed, these groins can also be used, as I said, to protect the harbors And I hope to see some examples. And here, let me see this figure. You see a permeable groin. You see these windows. They are introduced in order to be able to mitigate their impact because they can change the shape of the coastline significantly. Okay, now let me close this. So we will dedicate some attention to the groins more than to breakwaters because breakwaters you already discussed them with Professor Archetti. Another active measure that I want to discuss with you is beach nourishment or beach replenishment. This is frequently used today. It is, you know, it is a solution that is generating some concern because basically it doesn't solve the problem. It's a temporary solution, and moreover, there is to say that it's extremely difficult to find the proper material to replenish beaches because if you use a wrong material, if you use a material that is not really doesn't match the appearance of the original one, you get an intervention that looks very artificial. And it's not easy to find a sand that looks like the original one because you cannot take the sand from the immediate proximity because otherwise, of course, you would create an artificial erosion somewhere. So it is unlikely that you can move the sand from a place where the sand was accumulated. It is unlikely that you can bring back to the beach the sand that was originally in that position. Usually you have to use other types of sand that have different color, different size, probably. Also, keep in mind that beach replenishment is more effective if you increase the size of the sand grains. And but if you increase the size, of course, it doesn't look like the original beach. So it is something that it looks like environmentally friendly, but actually it is an intervention that needs to be frequently associated with other type of intervention to make it long-lasting. And also we have sand bypass systems. Sand bypass systems are extremely important because, especially in the vicinity of harbors, because what happens when you create an harbor, you build up an harbor, usually you have to protect the entrance, and you protect the entrance with groins. These groins are blocking the sand movement along coast and therefore are originating a significant erosion downdrift. And this is a problem because you have accumulation of sand updrift in the vicinity of the harbor, and then downdrift the harbor, you have erosion. So what they devised in order to solve the problem is the sand bypass, which means taking the sand from updrift and bringing it downdrift, therefore in a way replacing the original movement of the sand. I'll give you an example later on of an intervention that was done by using a sand bypass system after the construction of an harbor. It is indeed something that may be very useful and gives to you a nice example of how harbors and adjacent coastline are strictly interconnected systems. And this is also why we analyze these structures, these protection structures or protection strategies in an integrated way. And then we have the passive measures. Passive measures, we can call them seawall and revetments and berm protection. What are revetments? Okay, in this figure you see an example of a seawall, and at the foot of the seawall, seaward here, you see boulders. You see boulders. These boulders are protections of the beach called revetments. Student, give me 1 minute, please, that I have somebody at the door. This is the inconvenience of staying at home. Give me 1 minute. I'll be back soon. Sorry, students, here I am. Okay. So revetments are, as I said, these boulders that protect the sand of the beach. And these have a relevant effectivity. They are very effective in protecting the beach. Of course, their visual appearance is not the best. Okay, and berm protections are basically, you know what the berm is. Let me refer to a sketch in order to recall what is a berm, and give me 1 second. Here we are. So this is a sketch that I think I have shown to you in the last semester, where you can see a recap of the structure of the beach. And so the berm is basically placed, it's an elevation of sand that it's placed at the slightly above the limit of run-up. So if you look at the zone after wave breaking, you know that wave breaks when approaching the beach. And the zone that is comprised between the wave breaking and the beach is called the surf zone. The surf zone is extended up to this swoosh zone. This swoosh zone, which is not shown in this figure, it's the zone that is alternatively covered by the run-up of waves, and then they come back and they run up again. And this zone, which is alternatively dry and wet, it's called the swoosh zone. So you have the wave breaking zone, and then you have the surf zone, and then the swoosh zone. At the end of the swoosh zone, at a slightly higher elevation, you have the berm. The berm is a part of the beach that has a higher elevation with respect to the neighboring zone of the beach. In fact, very often you have between the berm and the land, you have a zone with lower elevation, which is called the runnel. And then you have the dune. The dune is it marks the part of the beach that is reached by waves during very extreme events. Okay, so the berm has a very important function because it protects the beach from erosion. And let me show you a figure of the berm. I think it is in this lecture here. Let me see. I think it is, I should use this one, sorry. I should use this figure here. Here you see an example of the dune. You see the higher elevation with vegetation. This is the dune. And the berm, you can see the berm here. You see this part of the beach with cobbles, and which is located at the end of the wave run up. This is the berm. It is extremely important. And sometimes we decide to protect it by putting cobbles of larger dimension, larger size. And this is not a revetment. The revetment is made by large, I mean, it's a massive intervention with boulders of large size, while the berm protection usually is a kind of reinforcing of the berm. Okay, let me go back. So these are the passive measures: seawall and revetments, berm protections. Now let me show you some schemes, a schematic representation of several direct measures for beach protection. And look at the legend here. So you have the original coastline. In the legend, it's the Harbour symbol. And then you have the emerging structure. You see how they are identified. The submerged structures with the dashed lines. And with the symbol that I am now pointing with the mouse, you have the protected breaks. What are the protected breaks? Are basically submerged protections, which are located where we create breaks between our interventions. When you place interventions like breakwaters and you allow breaks between them, you have to protect these breaks because there you have the concentration of waves and currents. And sometimes the submerged structures are protected with a signal, it's the black circle, because of course, to avoid that boats may collide with them. Now, the seawall, it's clear. It's a protection that allows you to hold the line. And here you have an example of breakwaters with protected breaks. So the breakwater is displaced parallel to the shoreline, and it's, in this case, it's emerging, but you see that there are breaks which are protected with submerged structures. They may be formed by placing their boulders, by placing other protections, like, for instance, by placing, by paving the sea bottom with concrete or other kind of interventions like geotextiles we can use in some cases. Now, the next one is given by a combination of breakwaters with weak submergence. We define weak submergence, submergence of about half a meter with protected breaks, and partially submerged groins. So in this case, we have a combination of groins with breakwaters. Breakwaters are submerged. We adopt submerged structures when we want to limit the visual impact. It's a solution for creating more environmentally friendly interventions. The next one is perpendicular groins, and you see here a displacement with different lengths of the groins. And in this case, we have, again, perpendicular T groins. There is written perpendicular here because the groins may also be inclined at an angle in order to better contrast the main wave direction. Now we have another solution with small islands, and of course the best solution is to be evaluated by taking into account the impact, the visual impact, and also the wave behaviors, which may bring us to adopt only one intervention, like groins, like breakwaters, or to combine them if we have several forcings that may change, for instance, in different seasons of the year. Okay, and then let's talk about replenishment. Beach replenishment is just bringing sand there. And as I said, we need to be careful about maintaining this kind of interventions, because of course, if you have a tendency to erode there, if you bring additional sand, then it's going to be eroded. But replenishment can be coupled with hard infrastructures. So, for instance, a possible solution may be that you put groins there, and then you speed up the process of moving the shoreline forward by bringing them sand, because it may take a while before groins reach a steady configuration. It may take a long time, and therefore with replenishment, you may speed the process up. And in this case, the replenishment is protected with groins and also with a protecting bar. The bar is, if you look at our sketch here, the bar is an accumulation of sand that is placed in correspondence of the wave breaking line. And it's also a protection, it offers a protection against erosion. And therefore, a possible environmentally friendly solution is to create an artificial bar. I go back, it is what is done here with protecting bar. And here we have other different solutions. So we have a combination of replenishment with groins and weakly submerged breakwater. And then here we have another solution of replenishment protected with groins, and we can also use T-groins. Now, here there is a long discussion of how this protection could be mixed. Basically, these are things that I already mentioned to you, so I don't think we have to discuss anything more related here, but instead I would like to spend a few more words on sand bypassing. Let me increase the font, sorry. So, and let me give you an example, a direct example here, the Tweed Sand bypassing project in Australia. I think this is really interesting because it shows a solution that was adopted in order to protect in order to, let's say, limiting the impact of an harbor. So let me see, here there is a project background, and here the harbor is here. See where my mouse is pointing. So it's located in a sheltered area, which is up to the estuary of a river. Then what they did, let me see if I can, yeah, I can increase the zoom. What they did, basically, they needed, in order to make sure that the boats could navigate from the harbor to the sea, they built these two seawalls groins, and they needed to build it because otherwise the bar created along the coastline, the submerged bar, could create problems in the navigation of boats. So what they did is to build these two seawalls. You can also call them groins because actually they were not built for advancing the shoreline. So the term groin is usually used for a protection measure for bringing the shoreline forward. In this case, it is an intervention that was built up in order to make sure that the bar was not developing, therefore allowing the navigation of boats. So you can also call it seawall. And but what happened, you can clearly see here. So they had a huge deposition of sand updrift, okay, and erosion downdrift. And this erosion also continued along this cape here, around this cape here. So they experienced erosion in these beaches, this one where my mouse is now, and this one. So what did they do? The idea was to restore the original movement of the sand. So the idea was to take the sand from here, where my mouse is now, and bring it on the other side of the walls. How to do that? Okay, let me now go back with a sand bypass. And basically, I didn't show this to you. Let me see. The erosion extended up to here. You see, they had erosion up to here in the left of the figure. And of course, with an impact on tourism and several activities. Oops, sorry, I closed it. Now let's see what they did. You see that this is after the intervention. Do you see now the situation, how much is different after the intervention, after the sand bypassing? See at the sand here on the left of the figure, at the beach, how it advanced. And you can see here now the morphology of the beach at the two sides of the seawalls. It's almost eliminated this gap originated by the seawalls. And let me now show you some details on this sand bypassing. Let me see, I think this video, let me just show you very quickly, because I want to show you how the bypassing was done. 1 second. Okay, here it is. So basically, okay, let's close this. Basically, the bypassing was done in this way. There is this long pipe, which is pumping water plus sand from the sea, and then the water with sand is taken along the pipe and transferred on the other side. Let me just show you. You see here, this is the long pipe that is pumping the sand. And I'm not sharing the audio because it is not really relevant. I just want to show you. You see the sand, which is pumped on the other side. And I think there must be a sketch of the paths followed by the pipe. Let me see. I'm looking for a sketch of the displacement of the pipe. I don't think it is here. Okay, let me just stop this and you can have a look at the video if you are interested. And now let me see, I think there are some pictures. Okay, but have a look and basically what they do is to bring the pipe on the other side of the river and then release the water with sand on the other side. Okay. Now, here there is a discussion on what are the limitations and in particular the issues that we should evaluate with attention when we design breakwater and groins. And I'm particularly interested in groins because, as I said, breakwaters are not our main concern. You discussed them with Professor Archetti. And the important thing that I want to point out here, it's what are the rip currents. The rip currents are currents that may be generated by groins, and they are currents that are directed from the land side to the offshore side, which are generated by the waves reflected by the groins. These rip currents are to be carefully evaluated because they may be dangerous for people bathing in the beach. And sometimes people don't realize this kind of risk, but I think that you may have heard several times of people that during conditions of high waves, high sea, they were not able to get back to the beach after having taking some bath in the sea. And these are conditions that are risky and are originated by rip currents. Here there is a Wikipedia page, and I think it is, you see, you see the an alert that is placed in a beach to explain what rip currents are. And again, they may be originated by breakwaters. So this is an issue that especially, I mean, especially when you have deep sea that is close to the beach, which is not the case for the Adriatic Sea, but it's the case for the Mediterranean Sea, you have to be very careful about rip currents that may be originated by groins. And when you are concerned by this possibility, combining breakwaters with groins, it's an opportunity. On the other hand, there is to say that one of the nice things, one of the benefits of groins is that they are more visual friendly. Because with respect to breakwater, groins do not limit your visual of the open sea. And this is a benefit that is clearly not so important, not so relevant when you combine breakwater with groins, because what we should avoid is to give the feeling that the beach became an artificial environment. I know that it's something like trying to hide the dust under the carpet, because it's clear that our beaches are all human impacted, are affected by anthropogenic activities. On the other hand, there is to say that if on the one hand, we don't have a pristine environment in most of the beaches that are in Italy, for instance. On the other hand, there is to say that it is extremely important when you have a human impact on the environment to make sure that the human impact is sustainable and environmentally friendly. So, I mean, when you design an an harbor, you design protections for the harbor and the beach, of course, it's impossible to keep the pristine conditions. It's a huge impact, which brings ships, maybe large ships, brings change in the wave hydrodynamics. On the other hand, it's also true that it's possible to minimize this impact. And then it's important to make a design that it's our highest expressions in terms of mitigating this kind of impact and making it sustainable. Okay, I think we can close here, because I think that, let me see. I think that here it is something that we already discussed. It is discussing berm protections and other measures like revetments, but we already discussed them. This discussion that we had today so far, as you see, it's mainly descriptive. It's an introduction to beach and harbor protections. It's something that basically you don't have to be concerned by at the exam, when preparing your exam, but it is extremely important that you get a clear overview of what's possible and what is the functioning of each protection, and what are the pros and cons of each solution. This is extremely important in order to introduce a more technical design that we will discuss in the coming lectures and couple of hours. The more technical design is, as you will see, still based on the use of empirical relationship. On the other hand, precisely because we use empirical relationship, it is extremely important that you understand the concept and the underlying dynamics. And this is the purpose of this discussion that I had in these first 2 hours today. Okay, at this stage, given that we have an overview of what's possible, let's talk about the design of groins, and by moving to the next one. I am making an introduction of about 15 minutes, and then we make a break. Okay, and let me say that here you see a permeable groin, and so let me say once again, by looking at this figure, where you see another example of a groin with a particular shape that was conceived in this way in order to offer a protection against 2 directions. 2 directions which are probably identified by looking at the dominant wave direction, and which may be characterized by 2 main directions. And let me once again say that groins are for both harbors and beaches an important structure. They are less artificial with respect to breakwaters. If you look at this shape here, even if it's clear that it's an artificial shape, it's in a way resembling what may be a natural situation with pocket beaches that are included between 2 rock formations, which may occur in a natural beach. So creating these pockets is in a way not so impacting as a breakwater. So they are indeed an important structure. Of course, they are important in relation to their specific functioning. If you have a dominant along-shore wave component, they are the optimal solution. If there is also an important cross-shore component, they should be coupled with breakwaters, or we may devise some shapes like the one that is presented here. In my opinion, it's clear here that there is a dominant wave direction along shore from the right to the left. But given that they also put this long arm of the groin, which goes in a way in the same direction of the dominant waves, it's clear that here they wanted to combine protection against a longshore sediment transport erosion with a protection against cross-shore sediment transport erosion. So it is, as I said, a structure that is an interesting opportunity. It is a structure that it's not easy to design because, again, we are talking about hydrodynamic processes that do not lend themselves to an easy description. And therefore, this is why we have seen the video before starting this lecture. This is why often we go to the lab and make experiments. On the other hand, there are rules of thumb that we can use. What is the concept behind it? The concept is that when you build a groin, which has a dominant extension that is perpendicular to the shoreline, you originate movement of the shoreline forward, which takes place because if you have an important longshore sediment transport, the groins trap the sediment transport between them. And therefore you have a movement of the shoreline forward. And what you can see here. It's clear that this beach was moved forward by the creation of these groins, because if you look at their position and the pocket of sand in the U shape, it's clear that this was stimulated by the presence of the groins. And if you look at the updrift direction, as I said, the waves are traveling from the right to the left, you see that the deposition of beach gets close to the top of the groin. Close, but not really to the top. In fact, this is something that we have to keep in mind. Usually, the new shoreline doesn't reach the top of the groin, but it gets to a distance from it. And this is what we have to determine. So determining the shape, the new shape of the coastline, it's our question mark here. It's our question. And again, I will provide you a rule of thumb, an empirical approach, along with the usual consideration that a more refined study, if needed, should be carried out in the lab. Okay, so first, groins can be classified as either long or short, depending on how far across the surf zone they extend. So, next selection. Groins that traverse the entire surf zone are considered long, whereas, third selection, whereas those that extend only part way across the surf zone are considered short. So remember, the surf zone is included between the breaker line, typical breaker line of waves, and the beginning of this swash zone. Swash zone, dry, wet, dry, wet. And it is called surf zone for obvious reasons, because it is where surfers have most of the fun. Between the breaker line, because then they can use the energy that comes from the movement of mass of the water. After breaking, waves transform from a movement of energy to a movement of mass. So surfers can get fun from the movement of mass, but of course surfers cannot go to the swash zone, because otherwise, of course, in the swash zone, they cannot navigate, they cannot surf. Now, so long groins they cover the whole surf zone. Short groins, they go only part way across the surf zone. Now, it's clear that these terms are relative because the width of the surf zone varies with the prevailing wave height, varies with the season, etc. But there is to say that usually we have a definition of the average surf zone that can give you an idea. Okay, now how to design groins? First, let's always keep into account that they are effective against the along-shore sediment transport, and let's also take into account that we may need some permeability to sediments. Why? Because a groin has a very significant impact, and of course you want this impact because you want to bring the shoreline forward. On the other hand, you want to make this impact, you may want to make this impact smooth, meaning that, for instance, if you place a battery of several groins and then you make them not permeable, it may happen that most of the sand is trapped by the first groins updrift, and no sediment is left for the subsequent ones. So if you want to make the final result smoother, especially if the intervention covers a long portion of the coastline, it may be advisable to start with permeable groins. And in some cases, permeability can also be characterized by flexibility. There are some groin structures where you can temporarily close the windows in the groin body. And this is something that has to be taken into account, and we will see how to take into account permeability in our rules of thumb for groin design. Okay, now let's make some preliminary qualitative analysis of groin functioning based on our experience. So first of all, how long does it take to reach the first results? And first, let me say that we have experiences that reported that for some groin interventions, the shoreline is still advancing after 30 years from the realization of groins. So it may take a long time. This is why we may consider coupling the building up of the groins with beach replenishment. Furthermore, take into account, as I already mentioned before, that groin interventions never bring the new shoreline up to the top of the groin. The new shoreline is always reaches a level that is always at a certain distance, and we will see how to estimate this distance. And why is that? Because there is a process which is called groin bypassing, which means that the sand that eventually may reach the top of the groin is transported by currents on the other side. This is quite intuitive. If you think about a displacement of sand that is located very close to the top of the groin with waves that are approaching the groin, then it is quite understandable. You may understand that some of the sand bypasses the structure. So this is why you don't reach with the shoreline the top, the head of the groin. And there is this effect of bypassing, which plays a relevant role. And also there is the effect of permeability, permeability, keep in mind that strictly speaking, no groins are fully impermeable. You have always some permeability because you may get waves that reach a wave height that is higher than the height of the top of the groin, and therefore you have some water basically mounting on the top of the groin and passing on the other side, which brings sand with it. So there is the combined effect of permeability and sand bypassing that you should always take into account. Now, so what are the parameters that determine the response of the shoreline to groins? This is another consideration that is extremely important. And basically, the parameters can be identified through a dimensional analysis, but we don't want to discuss this. I just want you to know that there are some analytical processes that may bring us to describe the process in terms of position of the new coastline, depending on a dimensional number, dimensionless numbers, through a dimensional analysis. I think that you probably have heard already about dimensional analysis, which is a technique that allows us through physical reasoning to understand what are the most relevant variables in a dynamic process. But again, I don't want to spend time on this. I just want to make a description of these behaviors, which can be divided in behaviors related to groin structure and behaviors related to waves. Let's make a discussion of these behaviors, relevant behaviors governing the new shape that is taken by the shoreline in the presence of groins. So first, we have the length. Long rather than short, of course, it makes a change, it makes a difference. Because as I said, the new shoreline doesn't reach the top of the groin, but of course, if the groin is long, you bring the new shoreline in a more advanced position. The spacing between groins, it's clear because we have already noticed that between groins, you get a U shape. And the larger the space between groins and the larger is the position, the larger is the position of the U with respect to the land. So the larger is the erosion between the two groins. There is groin elevation, which is making a difference. Of course, if groins are partially submerged or submerged, of course, it looks like they are more permeable. There is the porosity, which has an influence on permeability of the groins. Tapering is the shape of the groin, which may have a kind of conic shape with a larger width in correspondence of the shoreline, top width I'm talking of, and a smaller width as you advance into the ocean. The angle to the shoreline of the groins, and of course their shape, which I mean straight shape rather than T-head, etc. Parameters related to beach and sediments, which influence, again, the new morphology of the shoreline, are the depth, the sea depth at the head of the groin, tip of the groin, head of the groin, they are synonym. Beach morphology, slope of the beach, berm height, shape of the shoreline, etc. Depth at the average breaker line or beach closure. This is indeed the sea depth at the average breaker line. It's an important parameter, which also conditions the cross-shore sediment transport. Another parameter is sediment availability, grain size and variability, and sediment density. And then we have parameters related to waves, wind, and tide, wave height and variability, wave period and variability, wave direction and variability, of course, wind speed, wind direction, wind duration, and tidal range. Okay, I think now, before passing to drawing design, we can make a break. Do you have any questions so far? Let me see how many you are. 7. Okay, good. Okay, so let's make a break of 15 minutes. I'm not stopping the recording, so I don't forget to turn it on when I come back. Or, yeah, very good. Let me see. Okay, thank you very much. See you in 15 minutes. Okay, here we are. Let me share the screen. Do you have any questions, students? Can I ask you general question regarding, I'm not sure whether you are willing to, let me share the screen, to have just a very brief conversation on this distance virtual teaching. And I am interested basically in knowing whether you think that it's difficult to stay to attend these lectures in virtual mode, because my feeling is that for instance, today I'm lecturing 4 hours, and my feeling is that it's not easy to keep attention for 4 hours when you are in front of a screen. So in general, I would be interested in knowing your feelings, because if you have any suggestion to give in order to try to make this virtual teaching more useful, I would be very keen on receiving your suggestions. For instance, I am sure that my colleagues teach in a different way, and because of course we teach in a different way in any case, and I know that some colleagues are making an effort to reach a better interaction with the students, and sometimes I wonder whether what solutions could be adopted in order to make sure that you are happy with the teaching and you are taking the most of the benefit from it, the most possible benefit from it. So if you have any suggestion to give to me, like for instance, if you prefer that I make more frequent breaks, or if you prefer that we make more exercises, not sure what, if you have anything to tell me. And I don't want any way to, but if you have something to write on the chat, I would be really pleased to get your suggestions, or if you maybe send an email, because my feeling is that this year is different with respect to last year. And in the last semester, I was in physical presence, with the exception of Ravenna. In Ravenna, I couldn't easily move to reach Ravenna, and therefore in Ravenna I adopted the virtual teaching. But in Bologna, I was in physical presence with a reduced number of students, and it was definitely it was easier to teach because I could get a direct feedback from students. So, if I compare this semester with the second semester last year, it's different, because last year it was so sudden, the change, and everyone was stimulated to taking the most from it. And it was a new situation. It was a situation that required extra energy, and therefore the mobilization of extra energy basically made the interaction in a way easier. This year, you know, we are getting tired of this situation, and I'm not really sure whether I can be effective. Sometimes I have the feeling that I am boring. Sometimes I have the feeling that I'm not effective in conveying the concepts. It's so, to make it short, if you have any suggestion to give to me, I would really appreciate them.
Hey,
okay.
Professor, just a comment on that.
Yeah, please.
Yes, it's definitely more engaging to teach in presence, but at the same time, like even sometimes I definitely get bored with any lecture. But the good thing with this is that we could, because the lecture is recorded. Sometimes when I read something and I don't understand it, like because I was not paying full attention, let's say, I just go to the recording. So I mean, it has its ups and downs, I would say.
Okay, I see. You know that I was recording my lectures since 2014, so I have a long experience. So to me, it's not a new situation. And of course, I have to say that if you record from the PC, it's much it's more efficient than recording, because I use the camera or the phone before than that. So I think that indeed it was
more efficient to you. I would say that it's also more efficient to us, because with the echo in the lecture hall, it's quite difficult to follow. So, for example, if I wanted to follow half an hour of what you're saying now, I would put maybe the speed 1.5 or 2. It would be clearly understandable. While if it's a recorded lecture like in the hall, I mean, even at speed x1, sometimes it's difficult to follow.
Okay, I see. I see. Okay, this is interesting to know. And in any case, again, if you have any suggestion, and for instance, I was thinking today that probably I should prepare maybe a PowerPoint instead of following the lectures on the web pages, because I think that sometimes I need to be more focused and more brief in making some bullet points. So something that I can take into account maybe for the next lectures. Okay. Anyway, if you have any other suggestion, please let me know. It's sometimes I'm really hungry of interaction. You know, I really realized that it's a nice thing of my job is that is the interaction with the students, and I'm really missing it. Sometimes I feel like I am alone in front of the screen. So please don't hesitate to take the word, because it gives to me some motivation to become also more engaging, you see. Anyway, thank you very much. Let's move forward. Okay, so let me share the screen, and let me go to this design approach. And again, what I am discussing here now, it's something that it's related to the design of groins, and they are rules of thumb. So they are not analytical approaches, and not I would say, not very detailed approaches. And let me say that you know, there might be alternatives in both the field of numerical modeling and small scale physical modeling. So if you want to get something that goes beyond these rules of thumb for the design of groins, for the design of protection structures for harbors, then you still have these two avenues. Let me say that usually the numerical modeling is not adopted for the design of small scale structures and facilities, because you know, numerical modeling, it's good for getting an overview, but if you look into the details, for instance, if you have to design a single groin or a single couple of groins, you know, numerical modeling, the uncertainties are still very, very large. So in these cases, I think that for very detailed projects, small-scale physical models are still the best alternative. And also, you have to take into account that if you have to design a small-scale project, like it may happen to you in your professional activity, it's unlikely that you may get the resources to set up a numerical model, or even more, to set up a small-scale physical model. So the question may be, what is the best solution for me to go beyond the rules of thumb? And the suggestion that I may give to you is that there is a master experiment that you may make in order to study how the solution that you are designing it works. And the master way, the master solution, is to try it, to make a real scale experiment. So the message that I would like to convey is that when you believe that there is uncertainty in your design, and when you don't have the means to afford a very detailed analysis assessment, my advice is go with the rules of thumb and try to make a flexible design. This would be the best way forward. Like if you could make your design in a way that it can be subsequently adapted if something goes not wrong, but something goes in a way that is not what you expected. So what you may evaluate is the possibility to take a step-by-step procedure, a step-by-step realization, building up of your design. And an example that I always give to students, once I had to design a fish ramp for a river barrage, and I could find the solution to make it flexible. And this was really something that was helpful because fish ramps are really much complicated. Whatever solution you take, at the end of the story, you see that fishes don't go along it, don't climb along it. And therefore, the idea was in that case to make it flexible. So, and couple it with the monitoring program in order to see if we could find the right solution to make it working. And you may wonder, did it work? Unfortunately, the monitoring program ended before we could find a very efficient solution, because in the practical application, in the technical application, we also have these limitations that sometimes we don't have the resources for monitoring, and then we get stuck at a certain level of development. We make the structure, and then there are no resources, no subsequent resources to monitor it and to change it, to partially change it for what it's allowed. But still, I think that with beach structures, this would be really something interesting. Like, for instance, if you want to minimize the impact, use permeable groins with the possibility to reduce permeability. This is possible. Because if you use woody groins, then it's possible to reduce the area of the windows. And you will see that this is something, it's a level of flexibility that you can keep. So just keep in mind that we are discussing rules of thumb now. Keep in mind that there are alternatives if you want more details, but these alternatives are demanding. An alternative that we frequently overlook is the flexible design. And flexible design, I think it is also something very interesting and relatively new today. It's interesting because also with respect to people, with respect to policymakers, when you present something that is flexible, it is more attractive because everybody today is concerned by sustainability. And so if it's possible to make something for subsequent steps, allowing you some flexibility, I think this is really an interesting solution. Of course, it's not always possible, but with beach structures, it is possible. Because, you know, these are not hard interventions usually. I mean, it's unless you design a seawall, which is not flexible. But if you design breakwaters, if you design groins, for instance, you may make them partially submerged. And then if you realize that they are not effective, you can elevate them. And you can design them in a way that then can be elevated. Of course, this requires a careful preliminary evaluation. I mean, a flexible structure, a structure doesn't become flexible later. You have to design it to make sure that you have flexibility. For instance, if you want to elevate a groin, you have also to widen the bases. The base of the groin. As we will see, we will study the shape of groins, and if you want to make it high, you have to build it over a large base, and the base cannot be increased later because you have to put protections under the groin, and you have to build it in a way that it's already large at the beginning if you want to keep the flexibility to raise it up. Now, let me now discuss these rules of thumb. And there is a queen rule of thumb in designing groins, which is called the lambda shoreline. Let me emphasize it on the screen. The lambda shoreline rule of thumb, or you may also call it the 1/3 rule or 1/3 lambda rule. Also, I think you may also explore these references. I think they are open. They are, most of my references are freely accessible on the web. So what does this rule of thumb say? The rule, let me now explain it in words, and then I show you a sketch, okay? The rule says that the post-project coastline, post-project, during mean low water level, and we will see how to estimate it, is located between about, it's located, let me select it again. It's located between about lambda equal 1/3. So this is the reason for calling it 1/3 rule. And lambda equal to 2/3 of what? Of the distance between adjacent groins measured behind the structure's seaward face. Now, let me now look at a figure, okay? Now, let's go here, okay? Here you have a pre-project coastline. Let me show this figure. You have a pre-project coastline, which is located somewhere, and then you build groins. You see these groins have they are rooted into the berm, and sometimes they are pushed more inland with respect to the berm. And in fact, you see that you are putting the extreme end of the groin land side, you are putting it in a safe position. You don't absolutely want water bypassing the groin landward, because in this case it would be, you know, I'm not saying a disaster, but it would be a big problem, because if you have a bypass of waves behind the groin landward, it's a problem, because then you have a concentration of erosion there, and you have the formation of a channel into the berm, which is something that you don't want, absolutely. So usually we put the, let me call the root of the groin landward into the berm at a safe position. Okay, very good. And then we build the groin. This groin has a spacing that we indicate, these groins have a spacing that we indicate here with G. And this spacing is measured, if you have a T groin, a T head, it's the free space between the groins. You see how G is estimated here. It's the free space, which means that if you put a large T, you are decreasing G. Perfect. Now, the new low water shoreline, it's placed at a distance. So what you are expecting is that your sand moves seaward to reach a distance of lambda G with respect to the head of the groin, where lambda is taken equal to 1/3. Okay? So basically, this gives to you a real rule of thumb to measure what is the position of the new coastline. Here, I have also indicated the distance W between the low water shoreline and the high water shoreline, which depends on the slope of the beach. And this low water level and high water level are to be determined by analyzing tides, analyzing waves. And of course, the gentler the slope of the beach, the larger W, okay? If you have a very steep beach, W is not very large. But here the main message is precisely to say that you can estimate the position of the new low water shoreline at the distance lambda g from the head of the groin. And look at this figure, an important feature, two important features. First, this is of course not really the actual profile that you reach, because I already mentioned that you have a higher deposition of sand in the updrift side of the groin. So if you look at the dashed blue line in the left groin, you see that I have identified here the actual profile. So the actual profile is not really a straight line connecting the two groins. It's reaching the shape of a U, okay? And with a higher deposition on the left side in this case, which is the updrift. Updrift means that it's facing the coming direction of the waves. So it is trapping the sand. The groin is trapping the sand. And the second feature that I want to show you, lambda G, look at the right groin, which is T-shaped. Lambda G is measured by the extreme end of the T, which means that according to the lambda rule, you bring the low water shoreline more seaward if you adopt a T shape, okay? Because lambda G is measured by the extreme end of the head as you look in the figure. So this gives to you an idea of the position of the new shoreline, low water, meaning that of course, when you have, if you have a difference between low water and high water, for instance, it may be a difference in different seasons, then you have to also take into account that the lambda rule gives to you the position of the low water shoreline. It's, of course, a very empirical rule. You may say, but this is something that cannot be very reliable. Actually, I tell you, to give you an order of magnitude, to give you an idea, this rule, if you look at the figures that I have shown to you, you can recognize it. And you can recognize that it's not so mistaken. And we will see. We will go back to these figures later, just in order to get an idea, okay? And now let me go back to the web page. So, and let's now read again. The rule says that the post-project blah, 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 it's lambda may be varying between 1/3 and 2/3. Okay, so just keep in mind this, uncertainty, okay, which is, I mean, it's relevant, but again, it gives to you a very useful indication. Okay, larger lambda values, which may even exceed 2/3, may be appropriate for energetic environments, larger distances between groins, uncertainty in the long-term sediment supply, and the whole design process. So, what it is meant to say here? You see criteria for discriminating between, for moving into the range of lambda, for moving into the range between 1/3 and 2/3. So the criteria are, the characteristic that you have to look at are energetic environments. Energetic means that you have a lot of energy into the waves. So you have a larger erosion potential. Remember that the erosion potential is related to the energy of waves. So a more energetic environment means a higher capability of waves to mobilize sediments. And therefore, energetic environments try to be aware of the fact that you may have, it may take a longer time to reach the final configuration of the beach. And, you know, the intervention, the groins may be less effective. Larger distances, this is, of course, it matches your intuition. If you put groins very close, of course, it's more effective. On the other hand, you have an impact on the visual, you have an impact on the sustainability. You know, you don't like these solutions with very, very small spaced groins. And also, if you have uncertainties in the whole process, I mean, you may have uncertainty in the definition of the wave forcing, uncertainty in the definition of the sediment supply. Sometimes you deal with situations where you realize, maybe because there is a long experience, there are previous projects, you realize that uncertainty, yes, it's there, but still not so concerning. And in other cases, you really feel that, you know, you really know little of the context, the situation, and therefore, of course, you have to increase your safety factor. Increasing your safety factor means that you have to increase lambda. And if you increase lambda, it means that if you want to reach a considerable advance of the shoreline, you have to make longer groins, okay? Okay, and here you see, in general, larger lambda values imply a more prudent design. Good. Now, there is one more thing that I wanted to say. I already said that you may rely on flexible design, and this is a very practical advice that you should take into account. But there is one more thing that I wanted to say. When you realize that there is uncertainty and you feel like, I mean, you need some confirmation. So this may bring you to adopt a flexible design. On the other hand, take into account that, again, the real world experiment is the best way to check how a beach works. So the message is, if you have in the neighbors of your beach another beach where interventions have been already made, just look at what happens there. This is extremely important. Try to compare with similar situations. Of course, similar situations ideally are located in the same context. So a neighboring beach, it's the best solution. But you may also identify similar situations in other contexts which have similar behaviors. So try to look at what people already did. This is a general advice in design, but it is, I think, extremely appropriate when there is large uncertainty. And therefore, try to have a look, but not only when it's time to make a design. Try to have a look at situations. Try to go, for instance, in our beaches, if you have an opportunity, there are a lot of groins, a lot of breakwaters. Try to look at what happens there. And try to estimate if the lambda 1/3 rule works well. Try to see what people do, because this is another very useful advice. You have a problem, beach erosion, try to see in other contexts, similar contexts if possible, what people have done. And I will mention later another, for instance, I'm not sure whether I should say this now, because I think we will have other opportunities for discussing this, but I want to give you an example. I'm not sure whether you noticed that in the Adriatic Sea, which I know quite well because I used to go to the seaside there when I was a child. And I noticed sometimes I went to the sea during winter, and I noticed that people, basically on the beach was so different with respect to summer because they brought all the sand landward. So they went there with mechanical machines to bring the sand landward. And to an extent that was you know, the beach was looking very differently, and I didn't understand why they did it. Now I realized some years later that this technique is called beach scrapping, and it's a way to protect the beach from erosion. Why? Because erosion is more pronounced during winter in our climates, and so during summer you have quiet conditions usually. And they tried to remove the sand during the season when the sand is prone to erosion. So in order to lose it, they decided during the winter to move the sand landward and to reconstruct a sort of artificial dune. This is extremely interesting. So by looking at what people did, you realize that this is an excellent opportunity. If you want to protect the beach, this is a great solution. You reconstruct the dune, because keep in mind, on the Adriatic Sea, the dune was removed in order to facilitate tourism. But the dune it's an excellent protection against erosion. So they say, okay, when there are no tourists, let's build the dune again. What is the problem with this solution? The problem is that, you know, by moving sand, you destroy the ecosystem. You don't realize that there is a very active ecosystem into a beach, into the sand. But if you move it in this way, you destroy any vegetation, any microorganism living there. So it is not really environmentally friendly, but it's a good solution. Again, the advice is look at what people did. And in this case, let's look if this 1/3 rule is working. Okay. Now, consideration here. The rule is considered applicable when the angle between the wave crest and the line connecting the tips of the structure's control line is small. That is lower than 25-30 degrees. So basically, let's identify the control line. The control line, let me go to the figure. I'm sorry. Let's see if I can open in a new tab. Let me do like this. Let me open a new tab and let me get the figure in this new tab. Something went wrong, but no, it's fine. Just 1 second. I need to get the figure. Here it is. Okay, so what is the control line here? It's the line connecting the tips of the groins. So look at my mouse. This is the control line. Okay, now let's look here. The rule is considered applicable when the angle between the wave crest, dominant wave crest, of course, and the line connecting the tips of the structures, tips or heads, how you call them, control line is small, which means that what you should do is to displace the control line as parallel as possible to the dominant wave crest. And given that usually, you know, you use groin when waves are at an angle with respect to the shoreline, because you use groin when you have a component of wave velocity parallel to the shoreline. This means that it may happen that the control line is not parallel to the shoreline. And indeed, if you go to the previous figure at the beginning of this lecture, sorry if I scroll up, you see that here it's clear that the control line, it's not parallel to the shoreline. It's not very evident here, but let me give you another example. and the other example is a subsequent figure. And in this case, it's still parallel, the control line anyway. And but you see that the gap is approximately aligned with the dominant wave crest. This is the message that I want to give you. So the rule is applicable if the control line is almost parallel and or the angle is reduced 25-30. Let me go up again. And this is what I was saying. Okay. So control line, it's another term that we learned now. And now actually what is mentioned here, and you know, it's what I already mentioned. So the lambda shoreline rule would predict a rectilinear line shape of the equilibrium profile of the beach, but it's not rectilinear because, as I mentioned, settlement of sediments tend to originate a curved shape of the, a curved shape of the after project shoreline. So it's what it is depicted here in with the blue dashed line. Okay, so it's not rectilinear, I mean, clearly. Okay, good. Let's move forward. And let me also say one thing. We are not discussing here other empirical rules which may cite the application of the lambda 1/3 rule. We are not discussing them. But there are other rules which try to predict what is the curvilinear shape of the final displacement of the coastline. And you see this is another figure with another example. So you see here how lambda g is measured, and in particular with these two groins. So basically what we are trying to do is to draw a circle of the distance lambda g from the tip of the groin. And of course, this circle is to be connected with the position of the low water shoreline, which is determined by drawing a distance lambda g from the control line. Okay, this is the essence of this lambda rule. And then we can identify at this stage some practical steps, which I would like to discuss with you. They are many, like 10 steps, for the design of groins. So I'm now attempting to give you a technical guide of the steps that you have to undertake if you have to design groins, by now relying on our knowledge of this empirical rule, which sets the basis for it. Okay, very good. So now here is the steps which are again taken by this publication, which I found very useful. Let me see if it's linked in my list of references. Just 1 second. Because I believe it is available online, but I want to make sure of it. Let me see. I don't think it is. Let me see. When you want to find a publication, I think that you are expert already, but what you have to do to check if it's available on the web and also to get information if it's freely accessible or not, you should copy the title, and then you open a new page, a new web page, and you go on Google. Oh, sorry, not on Google. You go to scholar.google.com. Maybe that you already know it. This is Google Scholar, which is Google for literature references. And then we copy here the title, and then you get it. So let's see whether it's freely available. Let me see. No, this is just 1 second. I think it is, but I'm not really sure. Find the library, because I'm quite sure that I got it freely, but I am just checking. You see that you have to follow the links, and then I think, no, probably it's not freely available. You know that nowadays it's, I mean, the period of references that are not freely available is fortunately going to end soon. But I think it's for this one, it's not yet over. So it's not freely available. So I think that probably I could get it from a library. Okay. In any case, keep in mind this reference, scholar.google Scholar. Okay, and I think that you know it already. Very often you get a link to the PDF. This link, keep in mind that may be more or less legal, meaning that sometimes you find a way to get the PDF with an approach that is not really, how to say, it's not really open access, so you have to be careful. So usually when I put something directly linked from my web pages, it's open access and I checked it. You have to be careful in downloading material that could be present on the web, available for download, but may have been made available in a not fully regular way. So you are getting it, but you have to be careful in redistributing or in using it for any use that it's not strictly personal. Okay, now let's close this and let's go again to our steps. So step 1, which is something that you already know, it's estimation of the wave statistics, and we are interested in the wave angle. This is one of our main parameters, and also we are interested in along-shore sediment transport potential, which means basically all the behaviors of waves, wave height, wave energy. Wave energy is what matters, and if you have an extended data set, it's not a problem. If you don't have data, you know, you have to try to find alternatives if you don't have information to estimate at least the wave direction. And then you should look at the beach morphology. So you go on the place, and this is an exercise that you may make already now. Go to the place, see if you can recognize clues, signs of the presence of a dominant wave direction. Usually, especially if you go to undisturbed location, it's easy to recognize it, because you know the shape that a beach takes, it's a response, it's a reaction to the forcing that the beach is exposed to, and therefore, if you look at the shape, you can get information on the dominant forcing. So again, try to rely on observation and your capability to understand, which take into account that your capability to understand, it's not related to your experience, it's mainly related to your will, to your imagination, to your capability to be open and to get information. And sometimes if you don't understand, you don't have to be concerned. It doesn't mean that you don't have experience. It just means that probably you need to consult with somebody. You need to try to get additional information. But you will see that by relying on observation, especially when dealing with the seas, by relying on observations, you get some information. You get information on something that is going on. So this step is estimation of wave statistics. We know it. And step 2, identification of the extension of the intervention. So how long is the coastline you should displace your groins to? And you have to take into account the dynamics of longshore sediment transport. You can rely again on observation. You may see that erosion is concentrated in a small portion of the coastline. And that this may happen, for instance, think at the bypass project that I just have shown to you. It's clear what is the problem there. What is the portion of the beach where you have to be effective? And so you may look at the sediment transport gradient. You may look at the original shape of the beach. And then, of course, you have to take into account that the shorter the extension of your intervention, the better it is. And sometimes in some places, you will notice that there are just 2-3 groins which solve the problem. And especially if there are changes in the shape of the coastline, there are curves, there are places where you have a higher exposure to erosion. And then it's just necessary that you protect these places. And sometimes it's easier than expected to identify the extension of the beach. Now, step 3, you have to, and this is something relevant, identify the design location of the post-project berm. So where do you want to bring the coastline to? And then you place the berm there. Your new berm should be placed somewhere seaward. You have to define it, okay? By taking into account that, of course, the larger the effect that you want to induce and the lower the sustainability. Okay. Step 4, estimation of the post-project slope of the beach by looking at adjacent beaches. This is what I suggested to you. Look at what happens in the neighbors. And we should take into account that after an intervention, you will probably get a gentler slope, a reduced slope of the beach. And because you have a reduced wave energy reaching the beach. And so you have a reduced slope, okay? And of course, the higher the energy of the waves, the higher the slope of the beach. If you think of the Adriatic Sea, the slope of the beach is almost 0. But why is that? Because the wave energy is reduced. If you look, if you go to the Mediterranean, in the Mediterranean, even when you have beaches, the slope is higher. Why? Because there is more energy. So if with an intervention you are going to reduce the energy of waves, then of course you get a gentler slope. Okay, so try to estimate, because we need this estimate of the slope to locate low water shoreline and high water shoreline. Okay, step 5. Prediction precisely of the horizontal distance W between the mean low water shoreline and mean high water shoreline. And we should also predict the horizontal distance S between the mean low water shoreline and the berm. And so this basically it's a distance that it's determined by, again, you should look at adjacent beaches. You may look at the same beach before the intervention and take into account that you will have a change in the slope, a reduction of the slope. This is important because what you should identify is the position of the new shoreline, the position of the new berm. Okay, now let's go to a more quantitative design. Step 6, identification of the number of beach cells, N, and the average gap width, G. G, remember, is the width of the control line, okay? N is the number of cells. And then you have to identify the groin head width H. I think this is the same symbol that was used in the figure. Let me see. 1 second. I go to the figure that I have shown you before, those with the red groins. Okay, yes, it is the same symbol. You see, it's the same symbol. It's H is the head width of groins. In this case, it is a T-shaped groin, and therefore H is the width of the T. Good. Now, for T-shaped groins, H is greater than Z, where Z is the width of the groin main body, of course. I mean, if you identify with Z the width of the main body, then H is greater than that for a T-shaped groin. If you have a rectilinear groin, H is the same as Z. Okay. Therefore, the total shore front length of the intervention, L, which is composed by N beach cells, is expected to be, let me select it, L is equal to N times G plus H. Okay, of course, if you have different shapes for the groins, you have to make a summation of each gap length G and each groin size head width H. In this case, we assume that the N cells have the same geometry, so I can compute L as a product of N times G plus H. Okay, now, so step 7, design of the length and head width of groins H. Depending on the design position of the low water shoreline length, of the low water shoreline, and depending on the length and shape of the groin, as well as head width, okay, let me see, because I think here there is some, depending on the design position of the low water shoreline. Okay, sorry. Depending on the design position of the low water shoreline, length and shape of the design groin, as well as head width, are determined by applying the lambda rule. Okay, so basically, you have to place the low water shoreline at a certain level. So let me go back to the figure. Suppose that you want to bring the low water shoreline here in the figure, where it is placed in the figure, then you apply, in the case of rectilinear groin, the lambda rule to estimate the groin length. And in the case of a T-shaped groin, of course, you have to take into account the shape of the groin itself. And again, by applying the lambda rule, you determine the length of the groin and the size, capital H, of the head, depending on the position that you established for the low water shoreline. Good. Of course, a T-shaped groin allows one to reduce the groin width, as the T implies that the low water shoreline is shifted seaward, according to the lambda rule itself. If one wants to bring the low water shoreline up to the groin head, this is possible, but you need a T-shaped groin. And in fact, here it's written, then a T-shape should be adopted. And then lambda rule implies that H is equal to 2 lambda G plus Z. Okay, and again, H is greater than Z. In some cases, it may be required that the mean high water shoreline reaches the head, namely, what we write is H is equal to 2 lambda G + W. And if I want to bring the high water shoreline there, okay, and So I can say that in general then H is equal to 2 lambda G plus X plus Z, where X is somewhere between 0 and W, depending on if I want to bring only the low water shoreline to the head of the groin, or if I want to bring the high water shoreline to the head of the groin. And therefore, what I have to do is to increase H. You know, basically, this relationship here, it's saying that, I go to the figure now, it's saying that if you want to bring this low water shoreline or high water shoreline to the top of the groin, I have to increase the size H of the head. And in order to bring this blue line up. Of course, this brings to getting a carved shape for the low water shoreline. So you get, or the high water shoreline, you get these new shorelines close to the top of the groin only in the vicinity of the groin itself. Because, of course, between groins, the distance, the position of these shorelines remains dictated by the lambda rule, lambda G, measured with respect to the control line. But in the proximity of the groin, then you get the shoreline approaching the top of the groin. So this condition here, now I go back to the web page, this condition here is to be applied if you want to bring the shoreline, low water or high water, depending on the value of X. If you want to bring the shoreline to the top of the groin, this is the relationship to be used. And therefore, if you go to the overall length, you can write the expression for the overall length of your intervention in this way. So the overall length is equal to n, which multiplies g plus 2 lambda g plus 2x plus z, which you may further develop in this way by multiplying n times each addendum between parentheses in the above relationship. And then with further developments here, 1, 2, and 3, you get an estimate for G, which is the gap between groins, depending on what? Depending on total length of the intervention, L, number of cells, N, depending on X, remember, X is 0. If you want to bring the low water shoreline to the top of the groin, X is equal to W if you want to bring the high water shoreline to the top of the groin. Depending on Z, Z is the width of the body of the groin, and then depending on lambda. It may happen that you get an estimate of the gap that is too small. It may happen because, I mean, if you increase X, and if you decrease, if you increase, if you change the value of lambda, if you change the value of X, and if you change the value of Z, then you may get an estimate for the gap that is too small. And then, if the gap reduces too much, then a rectilinear groin may be adopted, and its length increased, of course, because another way for bringing the shoreline forward, as I said, with respect to the T-shape, an alternative to the T-shape is to get a longer groin, to extend the length of the groin. So, in practice, what we do is to select a number of beach cells n for identified value of lambda and desired value of X, in order to develop a physically reasonable gap with G. And keep in mind as another rule of thumb that G values less than about 20 meters are not generally recommended for the visual impact. And I mean, at least for recreational beaches, you shouldn't go under a gap you shouldn't adopt a gap lower than 20 meters. And it's I would say that 20 meters is a real minimum, because otherwise, you know, it's very, very reduced, the distance of 20 meters. Try to have a look at the beaches and you will see that usually the gap between groins is larger than that. This is a minimum number. And okay, and also remember, it's not only a question of visual, it's also a question of rip currents, which may be originated, may be more pronounced if the openings are small. And again, rip currents are something that you have to carefully evaluate. On the other hand, if you want to get an upper estimate for the gap, I would say that an upper estimate may be something like 100 meters. And, you know, of course, if you go beyond 100, then it's likely that you get something that it's not really effective, because it becomes a combination of isolated groins, and then also the lambda rule is not really reliable in these cases. Okay, and keep also in mind that we didn't finish with the steps, but regarding step 7, keep in mind that for recreational beaches, it is advisable that the head width are smaller than the gap width. So H should be lower than G, because otherwise, the risk is that you create a sequence of closed environments, which is not really good, because also the quality of water may be affected by this, and you don't have to create a sequence of closed pools, because you know, you have a deterioration of the quality of water and also the ecosystem in general, and it's not a good thing, and also the visual aesthetic. Now, step 8, positioning of the gaps and heads along a line that is S plus lambda G seaward of the target design berm location, whereas it's the distance from the new low water profile and the berm. Okay, so basically, once that you design the target berm location, you have, of course, to place the heads along a line that has this distance S plus lambda G with respect to the new berm. And then the next step is orientation of the gaps to make them more closely parallel with the average or principal crest orientation of the breaking waves at each cell. The aim is to minimize this angle, which should in any case not exceed the value, as we mentioned before, of 25-30 degrees. Okay, and pay attention to what is written here. If the terminal structure in a field of groins, we can call a sequence of groins a field of groins, employs a head on its downdrift side, it's better to offset it seaward than landward. Okay, and let me show you an example by going back to the initial figure. Here, you see that the downdrift side, if you look at these groins by looking at the picture, the main wave direction is from the right to the left. And what you can you can interpret these groins as a T-shaped groin. It is not really a T. It is modeled T. But what I want to point out is that if you look at the downdrift orientation of the T, it's seaward rather than landward. Why is that? Because downdrift, you have more erosion, which means that if in this case, this downdrift part of the groin was displaced with the head landward rather than seaward, you would favor erosion in the downdrift side. So it is important that when it is T-shaped, or anyway, when it's modeled, it's important that the downdrift, the end of the T in the downdrift side is pushed seaward to protect from erosion the downdrift side of the groin. Good. Okay. Here there is the explanation, but I think I already explained it. So let's skip this. Step 10. Now that we have displaced our groin, we have to predict the impact of extreme waves. And this is something that is extremely important. Keep it in mind. We are designing the groins with respect to dominant wave behaviors. Dominant doesn't mean extreme. Dominant means frequently occurring. Dominant means a situation that is very frequent, so it's not an extreme, because the dominant behaviors are those responsible for the long-term evolution of the beach. On the other hand, extremes are responsible for shocks. And we have to make sure that these shocks don't destroy what has been evolving in the long term. So a necessary verification that we have to make is to check what happens when there is an extreme event occurring. So basically what we have to do is the shoreline and berm locations are to be checked for extreme wave directions. So what we could do is, we cannot use the lambda shoreline rule to make this assessment. But what we should do in a way is that we should make sure of what happens to the berm when an extreme event may occur. And if we foresee that the berm could be completely destroyed by an extreme event, then it may be the case that we protect it, at least in the season where extreme events are more likely to occur. So I don't have a final solution to suggest for making this assessment, but in a way you have to try to make a prediction of what happens with an extreme event. And of course, this prediction is it shouldn't be made by applying the lambda 1/3 rule. It's a prediction that should be made by considering the max height that the wave could reach, the max energy that the wave could reach, and therefore this consideration allow us to reach some understanding of the exposure of the berm, of the risk to which the berm is exposed. And of course, we have to make sure that an extreme event doesn't destroy an equilibrium that we may have reached in the course of years. Okay, now step 11. The landward head of the groins are extended to reach the berm and buried within the beach field. Perfect. As I told you, you have to reach the berm and maybe also some more, okay, in order to make sure that you feel safe against waves bypassing the groin landward. Step 12, the elevation of the heads should be determined to minimize wave overtopping during the design event of interest, which typically includes typical seas at higher high tides. So what does this mean? You have to make sure that for a reference event which corresponds with the higher high tide, the groins are not overtopped. So you may allow that the groins are overtopped during an extreme event, but you have to make a verification of what may be the impact even during an extreme event, but you can tolerate groin overtopping during an extreme event, but you shouldn't allow overtopping in situations that are likely to occur every year. So you basically should make sure that you don't have groin overtopping when you have higher high tides, because if you have in this situation the superimposition of some energetic waves, of course, it may originate the movement of the sand from one pocket to the neighboring one, and therefore the whole equilibrium of the new beach may be impacted. And the elevation of the stems, it's the part of the groin, the end of the groin that is placed landward. So the elevation of the groin landward may be lower than the heads, but sufficient elevation to prevent tidal overtopping at higher high tides. So again, it shouldn't happen that the groin is bypassed landward during high tides. Okay, and the profile elevation of the terminal structures should be higher than the design beach profile predicted to the structure. Of course, you don't have to bring the new beach profile very close to the structure in terms of elevation, and unless you are getting into the berm. And in the case of a rock structure, this is another rule of thumb, the crest elevation should be not less than 1/2 armor stone diameter above the predicted design profile, plus some contingency. So basically, if you make a groin by assembling boulders, the crest elevation should be not less than 1/2 boulder diameter above the predicted design profile of the beach. Okay, good. Now, here we are with these 12 steps. What I would like you to do is, to get ready to summarize these steps in front of a possible question at the exam, because I mean, it is. I understand that remembering 12 steps, it's a bit of an effort. On the other hand, this is mainly descriptive, with the exception of, I'm going back, of step 7, okay, where very simple calculations are done. But this is a question that I may ask at the exam. So the question may be, what is the gap that you should give to groins in order to bring the high water shoreline close to the head of the groin themselves? This is a possible question. Okay. Do you have any question so far on this step-by-step procedure? Let me have a look at the chat. Okay, now, typical dimensions. I have 5 minutes, 7 minutes to go before we try to make a closure. I'm going to stop at 1 o'clock. Typical dimension of groins. Now, first, let's look at this cross-sectional view of a groin. What you see, it's the presence of a foundation. So you can put just the boulders in the sand without preparing the base of the groin. And this foundation is basically aims to prevent instabilities, because if you just put the groins in the boulder in the sand, you may have instabilities, because you know that water is able to rapidly excavate in the presence of sand, especially at the foot of structures. You may have local erosion. So what we aim to place is a foundation which may be realized with different materials, including geotextiles, which are a very environmentally friendly solution. And then we have the structure that is formed by a core plus this is in this case it's stone groin. So there is a core, which is typically a material with reduced permeability with respect to the stones. And then over the core, it's placed a coverage of armor stone. Here you see the indication of some main sizes. There is the top width B here. And also you see an indication of the mean sea level with an indication of the submergence from the foot of the groin to the mean sea level, H, lowercase h. And you also have an indication of the height out of water of the groin, indicated here as RC. So let's give some orders of magnitude for the size of a groin in order to identify in a way the structure. So H, which is the depth of the basement of the groin head with respect to mean sea level, it's from 2.5 to 4 meters. 4 meters, it's already, it's a huge groin. And of course, the higher the groin and the higher the risk of instability. So you have to be careful in adopting massive structures. RC, which I just mentioned, height of the groin top with respect to mean sea level from 0.5 to 1.5 meters with respect to mean sea level. Keep in mind these orders of magnitude, because I may also ask you a question at the exams about them. Depth of the groin basement landward with respect to mean sea level, and this is landward, okay? And it's we mentioned that in the landward side, the height of the groin can be reduced. In fact, we see that the range is from 1 to 2 meters compared with the same range at the groin head, which is 2.5 to 4 meters. Okay, now width of the groin top, which is from 3 to 6 meters. 6 meters is a lot. And the slope of the groin sides, it's from 1.1 to 1.2. It depends on the material. So if you use boulders, you have to carefully check the stability of the armor units. We will dedicate a lecture to that. The thickness of the foundation is from 0.5 to 1 meter. And here you see the note that stability should be verified against extreme sea conditions. And we will talk about the verification of stability of rock and armor units. Now, one thing, those of you who attended the lectures in coastal engineering that I delivered last fall, remember that we had a discussion on beach hydrodynamics and morphodynamics models. They are mathematical models that describe the evolution of beaches, and they are based on the computation of the along-shore sediment transport. And we consider the application of the one-line model, if you remember. Basically, this kind of mathematical models, as I mentioned at the beginning, can also be used to describe the beach evolution after the building of groins. And this is a way, as I said at the beginning of the lecture, to verify through numerical modeling what's going on. And again, it's something that usually it requires a lot of resources because we consider the application of a very simple model, but these very simple models are not really the best solution that we may adopt. And you may remember that we talked about this model here, and let me see. It's the one-line model, which is basically based on estimating the movement back and forth of the coastline. I think that we don't need to go into the details here. I just, it is reported here, but it is something that you can read for your interest, but I'm not asking anything at the exam. But there is one thing that instead I want to draw your attention to, which is the analysis of groins by passing. So how can we estimate? How we can estimate groins by passing. And so here there is an empirical formulation which I would like to bring to your attention. And please remember it because this can be asked at the exam. And so this is an empirical formulation that allows you to estimate the fraction F of sand that is transported over a groin and through it. So over a groin and through it means taking into account the effect of bypass and permeability, okay? And so in general, we have permeability factor, P, and which it's an independent variable of this relationship because, again, we want to estimate the fraction F of sand in fraction of what? Of the long-shore sediment transport. So let's suppose that you have estimated the sediment transport along shore. You put a groin there. You are not assuming that the groin blocks everything. The groin will block a fraction, F. And this empirical formulation expresses F as a function of P, permeability, and a bypassing factor B. This is the very simple formulation, okay? 0, P and B vary in the range 0, 1. So P is permeability. Again, it's estimated depending on the shape of groins and in particular the presence of apertures in their cross-shore direction. So you may adopt P values that are suggested by the literature for different shapes of groins. And of course, groins made by boulders have a very little permeability and their P is close to 0. And you may estimate the permeability if you have a regular geometry with windows with apertures. You can estimate the ratio between the area of the apertures and the area, the total area of the groin. So the larger the windows, the larger the permeability, the larger the permeability. So this P is something that you may estimate by looking at the geometry of the groin, and then then the longshore sediment transport can be computed in this way. And And then there is the bypassing factor B. And B can be computed with this relationship. What are DG and DLT? DG is the sea depth at the groin seaward end. And DLT is the depth of active longshore sediment transport, which can be assumed to be about 1.6 times the significant breaking wave height. So you see that the larger the sea depth, dg, the lower the bypassing factor. Okay, which is quite intuitive. I think I can stop here. Let me just, there are some final considerations which I don't think we need to discuss because they are already part of what I discussed with you. Okay, students, it has been another very long day. So I wonder what is your feeling, and I wonder if you have any question. Let me look at the chat.
Hello, Prof.
Yeah.
I actually have no questions, but I wanted to give a small feedback about the teaching.
Yes.
I think that it could be really helpful for the attention if you can use the virtual blackboard for the explanations, also for small drawings and formulas, because I remember that you used the blackboard for the coastal engineering in fall. I followed the course, and I found that was really, I mean, the most similar thing to the in-presence teaching.
Okay, that's a good solution, a good suggestion. Thank you. I will try to do my best. I think that what I could do indeed is I could put the figures that I want to discuss in the blackboard, and I can put notes over there. Yeah, could be. It's something that I will evaluate. Okay, very good. Thank you. And other questions? Thank you very much indeed. I really appreciate the suggestion. Okay, students, let me stop the recording.